Okay, this is the first set of charts talking about the history of astronomy. And basically, the point being is the following. So, this is something you need to think about. Why would knowing astronomy be useful? Way back when and now. That's the thought. And for my in my face-to-face classes, what I do is ask them to think about these things, write it down on a piece of paper, and we would discuss it, and this would be part of their attendance. I do not believe in just if you show up, then you're counted for whatever and gain points by just being there. No, I want your mind too. So here are a couple of questions that you could use for the discussion exercises that we've assigned for this class. So, in prehistoric times, everybody observed the sky, and I think I talked about this in the Stellarium introduction as well, is we are quite disconnected from nature. And basically, this disconnect has allowed us to be more survivable, if you will, but it's also made us much more dependent upon our technology. For example, those that go out on backpacking trips and things like that do have to learn about navigation, and knowing what the sky looks like at night helps in that navigation. My girlfriend and I have done this a couple of times where we did not believe our GPS, we did not believe the compass. In one case, we saw water flowing uphill, and in the other case, I saw Orion's belt and Orion in the east when, identified it being in the east, and that got us straightened out. So this can be a life and death matter if you go outside of our technology. So when we started settling down, we built monuments, and here's a picture of Stonehenge, as it says on the first day of summer. Basically, Stonehenge has a whole bunch of monuments built up, and if you will, it can be used as a means to figure out when certain objects will rise, in particular places on the horizon. So here we have the first day of summer, the sun arising right in between those two monoliths. The Mayans had a calendar that was based upon a whole bunch of different cycles, and we've learned in the preceding chapter that cycles are the basis for us telling time. The Mayan long count calendar in its connection with 2012, don't mind that, but the Mayans used calendars to suppress their population as well. Basically, those people in charge of the calendars knew when it was going to rain and when it wasn't, and so they would stand out very highly when they predicted the rain. So be aware of those that know stuff, okay? At any rate, sometimes these monuments can just be pretty pictures. A student of mine found this picture on the Astronomy Picture of the Day. It is a piece of artwork, if you would imagine. Some of those lines do or are associated with when stars rise or set. But a lot of those are just spokes in a wheel, and they look pretty. The Egyptians did study astronomy for practical reasons, particularly because the flood of the Nile was a yearly event, and it pays to get out of the way of a flooding river, as those people, along the Mississippi know. And if you go canyoneering, you want to get away from very fast-moving water. They were the first ones to come up with a sundial and the first to come up with a 365-day calendar. Basically, we have a bunch of cycles out there, lunar, daily, and yearly, and they don't really match up that well. The Chinese, from them we've noticed that they have made observations of sunspots and supernova, and they do have an interesting calendar based upon Jupiter. I don't know why it was like that. Maybe somebody can find that out for us. The Babylonians they took lots and lots of measurements, and it's from them and the Greeks, by way of Alexander the Great, that astronomy really took off. As is the case a lot of times when one conquering civilization absorbs a bunch of other civilizations, that information sort of spreads around in the environment and new and different things happen. And that's normally when you make advances, is when new information meets new ideas. Here we have the Greeks again, and basically the point of this chart is, well, gee, that vase is really beautiful. But they're the first ones to come up with the idea that you don't need supernatural occurrences to explain nature. Just simple rules will work. And if you will, nature plays by certain rules, and the second thing is we can understand them. And here is our, pat on the back to Alexander the Great. He connected the Babylonian knowledge to the ideas that the Greeks had. And here's a picture of 5 planets. Mind you, we have 7 planets. The days of the week are named after them. And you can go with a combination of English and Spanish. That works the best. So, here we have a picture of the 5 planets in quotation marks. But think of the days of the week. We have Sunday. We have Moon Day. And then if you go to the Spanish, and my Spanish is horrible, I should have studied up on this, but we have Viernes, Miércoles, Jueves, and then we have so we have Jupiter, Mercury, Martes for Mars, Venus, and then that gets us through the days of the week, and then we have Saturday for Saturn Day. So I've gone through the days of the week, and that's how they're just commemorating the planets. And the planets are those things that do not move regularly with the stars. The planets, including the sun and the moon, do not move with the stars at all. The stars seem to be fixed, and so that's why they call them planets or wandering stars for these planetary things. And if you look at the moon relative to the stars at night, you see that the moon does move. It will take about 10 minutes, 15 minutes for you to recognize that movement, but it does move. And when you make the observation, observe the moon relative to a star. First of all, you'll notice that the stars don't move relative to each other. They sort of move along, and you can think of that being because of the Earth rotating on its axis. But you'll also notice that the moon moves relative to the fixed stars. Okay, Anaxagoras, he's one of these Greek guys, and he was the first one to suggest the celestial sphere. And the celestial sphere is what I'm talking about here. When you go out at night, it seems as though you have all these little bits of light up in the sky, and they seem to move all together. It's like, you have a big a sphere around us, like, you're inside of a ball, and on the inside of this sphere you have little dots, and all these dots move together. Now, the second part of this chart indicates that he thought the Earth was a cylinder, and that there was this axis east-west, and I thought that was a bunch of hokum or ridiculous. And I have since learned that his idea of a cylinder was basically that he thought the Earth was flat. It had some thickness like a disc, okay, but it was flat. And for being a Greek and being, having to deal with Greek sailors and stuff like that running around, this, anybody that's on the ocean knows almost for a fact that the Earth is a sphere. It isn't flat at all. So I'm kind of surprised, with this Greek anyway. Anyway, Pythagoras is another guy that comes on the scene, and his basic ideas were the world or the universe was rational, the cosmos was perfect, and therefore the Earth had to be a sphere. Okay, so that was his reasoning. Because of this perfection, therefore the Earth is a sphere. Putting ideas in front of observation is sort of a problem. Aristotle basically had some ideas, and a lot of them were wrong. And it took a long time, 2,000 years, before we got out from under this guy's thumb. But, here we have the four elements, sort of reminiscent of a very good band in the 60s and 70s. And there was this fifth element called the ether, which included all the heavenly bodies. And his idea of motion was that everything moves by something else. You have pushing agents, but also you have motion that is sort of intrinsic to the material. Basically, everything that is earth-like wants to be together. Everything that is fire-like wants to be together. And everything that is water-like wants to be together, and the same for air. So you would explain a fire in a couple of pieces. Basically, the fire is composed of a couple of different things. Things that are air-like, a campfire, is air-like, and so you get smoke rising because it's air-like. And then you have the ashes, which are earth-like, and they fall down into the earth. Now, he also did some pretty amazing stuff. He did put the Earth at the center of the universe, and he did prove that the Earth was round. Now, proving something is kind of problematic in science. We have better reasons for believing certain things versus worse reasons for believing things. But anyway, basically, he knew that the lunar eclipse was caused by the shadow of the Earth, and if you look at a lunar eclipse, and we're going to be without one for a few years now, it being 2016, you will see that you never see a lunar eclipse being a line. So if the Earth was flat, and the shadow was caused by the sun, okay, the Earth's shadow was caused by the sun, then depending upon how you oriented the Earth and the sun together onto the moon, then you could have a line or a square or a sphere. But always do you see a circular shape on the moon. And this is pretty neat to see. You should go and see it sometime. All right. Next on here, we've got the statement that Aristotle's ideas ruled for 2,000 years, and it was really hard to get out from under it. Aristarchus is the guy who actually measured how big the sun was and how big the Earth was Eratosthenes, and this is a pretty amazing trick. And I'll go into a little bit more detail in this topic a little bit later. But just amazing. It gives me goosebumps to think about it. Okay, Hipparchus made the first detailed observations of stars, and we'll continue to use those. And if you look at Stellarium, that's why we have different names for the stars. Sometimes, and it's dependent upon the catalogs that people make. And from looking at these catalogs, we see that the stars actually move a little bit. They do move relative to each other, but a little bit. And it takes centuries to actually observe, unless you have really fantastic technology like we do. He defined the idea of categorizing the brightness of stars, so this idea of magnitudes, and the magnitude is basically a first magnitude star is brighter than a second magnitude star or a third magnitude star, sort of like first place, second place, or third place for a running contest. He also had this idea of epicycles to explain the planetary motion. And we'll be looking at that in Stellarium a little bit later. But an epicycle is described here, and basically the idea that Hipparchus had is everything moves around the Earth, and you have these circles upon circles. If you remember Pythagoras, basically a circle is a perfect figure. And so in order to describe the motion of the planets, because the planets do move oddly. They move nominally opposite to how the stars move, the opposite direction. But sometimes they move in the same direction. Now there's a little game, let's see if I can remember its name offhand, having a senior moment. I guess it's the moment's here, can't remember. Anyway, we'll continue on. Ptolemy came later, basically around the time of the Caesars and Christ, and he used epicycles to explain everything. He needed like 88 epicycles to describe the motion of the planets at that time. I think you are required to have like 3 to describe the motion of the sun, and then another 3 more to describe the motion of the moon, and then you need like 5 for each planet, maybe even more. But the idea is that you need a lot of these circles running around each other in order to explain that motion. It turns out it is pretty accurate. We use a similar sort of thing, and it's called Fourier analysis. But the basic view that the Greeks had were these 3 things. There's no apparent motion on the Earth. The heavens are perfect and unchanging. There is no stellar parallax. And that means that the stars appear to be the same independent of season. So the idea was this. Compare this notion, all these things seem relatively reasonable, with the idea that the Earth is the center of the universe, or that, if you will, the Earth goes around the sun. If the Earth goes around the sun, then you would expect to see the stars sometimes getting, being a different distance from each other, a different angular distance from each other, and then sometimes they would be closer together, sometimes they'd be further apart. And we don't see that. Now, the reason why that we don't see that is that these stars are really, really far away. Okay, so the experiment that I do in class with my face-to-face students is I put 2 objects close together, and I ask them to measure the angular separation between them using what's called the pinky rule. And we'll see if we can do that in our online class. Now, there's no apparent motion on the Earth, and you look outside, and yeah, it doesn't move. Now, naturally, if you're with your significant other, it does move. But be that as it may, if you go outside, if we were going around the sun, then we would need to go about 33 kilometers per second in order to make that motion around the sun. And if you go outside, you don't feel a wind going at 33 kilometers per second. Okay, 33 kilometers per second is really darn fast. Okay, consider a car. It's going about 60 kilometers per hour. Okay, or 60, if you will, 60 kilometers per hour is about 50 miles, per hour. Okay, so if you now multiply that by 4,000 times, right, you get a certain sense that you would not be able to stick your head out the window. Okay, and so the idea that there's no apparent motion on the Earth seems pretty reasonable. And then the other thing is, if you look up at the heavens, they don't change. Okay, certainly over a generation, they don't change. So this is their basic view, and this led them to believe that the sun was not the center of the solar system, but that the Earth was the center of everything. All right, so the thing I want to show you is this, well, I guess I can't show you, but I'll stop right here, and we'll continue a little bit more once I've gotten these simulations to work. But these simulations that I want to show you are based upon Ptolemy's idea that the Earth is the center of the solar system. And that puts quite a lot of restrictions on how you then explain the motions that you see in the sky. So remember, models are here to explain nature around us, and these models allow us some predictive ability in reference to our observations. Okay, so we can predict tomorrow what we should see, and then tomorrow we can go and see what we see and compare that to the model. If the model is right, then then we're happy. And in fact, if the model is wrong, then we're even happier, because then that means we can get a Nobel Prize. All right. So talk to you later, guys.